Good afternoon, everyone, and welcome to our live seminar series. My name is Olivia Lanes from IBM Quantum, and I am very excited to be here today and to be able to introduce today's speaker. Guanyu Zhu will be talking to us today about quantum error correction with non-abelian topological codes. But before we get started, I'll just give everyone a few moments to tell us where everyone is tuning in from today. I am actually tuning in from our lab in Yorktown Heights, New York, which you can't tell from my very nondescript background. But yeah, just everyone, let me know where you're tuning in from, and we'll just give every minutes before we get started. Okay, awesome. Hello from Toronto, Manhattan. That's not too far away. Just give everyone a few minutes. All right, I think we are just about ready to get started. All right, great. So hello, everyone. My name is Olivia Lanes from IBM Quantum again. We are thrilled to roll out the latest episode of the Quantum Seminar Series dedicated to the research and the academic quantum communities. The seminar takes place every Friday at noon Eastern Time and is hosted here on the Qiskit YouTube channel, so make sure to subscribe if you haven't yet. Like I said, I'm your host for today. My name is Olivia, and I'm very excited to be here and to be speaking with Guanyu Zhu, who will be talking to us about quantum error correction with non-abelian topological codes. All right, so welcome. We're really happy to have you here today. I'll give you a very quick introduction, and then we'll get started. So Guanyu did his Ph.D. at Northwestern and then moved on to a postdoc at the University of Maryland. After the completion of his postdoc, he joined IBM Quantum as a research staff member in 2019. He works at the interface of quantum computation and information theory, condensed matter theory, and AMO physics, but the focus of his research includes the interface of quantum information theory, condensed matter physics, which includes quantum error correction, topological quantum computation, many-body theory, and superconducting qubits. All right, so thank you so much for being here today. How is it going?
Great. Thanks, Olivia, for the introduction. So shall I start?
Yeah, please get started. And if anybody has any questions, feel free to ask throughout, and I will do my best to very quickly interrupt you.
Okay. So today I'm going to talk about quantum error correction with non-abelian topological codes. And this work was done in collaboration with Alexis Shorty, Leander Bergman, and Frank Verstraat from Ghent University in Belgium. And recently, Alexis Shorty just moved to IBM as a postdoc. So you can also find a preprint here. So first, so I would like to start this talk with a metaphor by John Preskill, which was quite inspiring. So this is the quantum book metaphor, which can also be found in this paper. As we all know, quantum information is very fragile against the noise from the environment. So in order to protect the quantum information, so we can introduce a redundant number of qubits, which are the kind of the pages in this quantum book. And so the information is not stored locally. So if you read each individual page in this quantum book, you just get no information. So it's blank. So that means no information in individual qubits. But we store the logical quantum information in a highly non-local way, which across the as a correlation of a highly entangled many-body states of these qubits. One example is the topological state. So in this way, the environment cannot easily measure or decohere the local logical quantum information, since typically the noise is quite local. So now we come to the concept of topological quantum computation, which really use this idea of non-local encoding. So the original proposal by Kitaev and Michael Friedman is to use Anion to perform fault-tolerant quantum computation. And there are mainly two major approaches to do topological quantum computation. So one is the so-called passive approach, which is also the original version. And in this case, when the information is encoded in the ground space of certain exotic topological state of matter, which could be found in nature, and that includes something like Majorana wires, fractional quantum Hall states, or quantum spin liquids. And in this case, the information is protected by an energy gap at zero temperature. So the noise in this case will create anion, but that causes energy. So that's forbidden at the zero temperature. But unfortunately, at the non-zero temperature, there could be thermal noise, and the passive topological protection cannot protect against the thermal noise. So in this case, one still need to do some active error correction to fix the thermal anions. And also in this context, the way to do a universal quantum computation, one of them is to braid certain exotic non-abelian anions. And then it comes to the another approach with the active quantum error correction approach, which is considered to be more practical at the current stage or in the near term. This include the case of a service code or the Tory code, which is essentially the same thing but with different boundary conditions, and other thing like color code. So this approach, the central idea is to simulate the topological state of matter in nature in our quantum computer. And so the information now is encoded in the code space of a quantum error correcting code, kind of living only in some ordinary qubits, where you don't need exotic qubits like Majorana wires. And you do active measurement of the error syndrome, which in most cases some stabilizers. And when this error syndrome or stabilizers are violated, you perform error correction and to bring anion back to the ground state or the code space. So in this talk, we consider an active error correction with the non-abelian anions. So that's a little bit different from the majority of the topological codes. So the idea again is to simulate the non-abelian anions in nature with our quantum computers. So we consider a code space of a system of just ordinary qubits. There's no topological materials. And we do active measurement of a set of commuting projectors, which are the error syndromes, and similar to the case of the stabilizers in the usual abelian topological code. And we, in this case, the noise will create non-abelian anions. So these guys are both blessing and curse. It's blessing in the sense that by braiding these non-abelian anions, you could perform universal quantum computation, but they are also the noisy system where you want to correct and want to annihilate the unwanted non-abelian anions. So our main goal is to construct such a non-abelian code first, and then also to perform a classical simulation of this code to show, understand its property. So the necessary ingredients of our work lies in the use of concepts in quantum error correction. And then another thing which is the tools in the topological quantum field theory, TQFT. And also the use of tensor network, TN. So, and we are in the interface of these things. So just to use a code, new wine demands new bottles. Since it's relatively new substance, so you need a sort of a new formalism using TQFT or tensor network to understand it. So to further motivate us, so why do we even want to study these codes, these non-abelian topological codes? So here we just have a brief comparison of them to the usual abelian topological codes, such as the topological stabilizer codes, including surface codes and color code. So there's both pros and cons in both situations. So the pros in the abelian stabilizer codes is that you have usually a low-weight local stabilizer code. It's quite simple and it's well studied, and they typically have high thresholds and make them very practical. But there are also some bottleneck in this direction, is that there is no native non-Clifford gate in 2D. So it typically can only perform Clifford gates in a two-dimensional setup, which is the current device people are pursuing, like IBM, Google, or other companies, also in academia. So then you need some extra non-topological operations, such as the magic state distillation, to perform this non-Clifford gate. Or alternatively, you can also do a code switching to some higher dimensional topological codes, for example, in 3D or 4D. And then this both approach could lead to high overhead, and also we probably need us to change the architecture. Although I would say they are the magic state distillation is currently still the most practical approach, and also the idea to go to higher dimensions is also very interesting, and I also spend a lot of time to study that. But in this talk, we are trying to find a different approach. So then for non-abelian codes, so the advantages are really to differentiate with this case is that it can perform native universal gate just in 2D by braiding the non-abelian anyons, such as Fibonacci anyons, which emerges from your code space as excitations. And they are beyond the usual stabilizer codes. So that's only the advantage for theorists. That means you can study more physics or more theory while studying these codes. But also there's cons that seem to be quite complicated. But this kind of thing could change along the time. So when you understand their properties better, you could actually simplify them. And they also seem to be hard to simulate classically. This is also due to that they are beyond the stabilized formula. So that's why we need those extra theoretical framework like tensor network and topological quantum field theory to classically simulate it. So there's additional question is whether there is actually a threshold in this kind of code. So this question was not answered before, and the main purpose of our work is to try to give an answer to this. And we actually find indeed there is we can compute an error threshold for this type of non-abelian topological code, and that makes this whole thing much more practical, at least in the long term. So the type of non-abelian code we will study today in this talk is called the Turaev-Viro codes, and there's a pretty long history of this code. So let me just have a brief review of the history. So it can actually be traced back to 1984 when Jones discovered his famous Jones polynomials as a knot or link invariant. And then later on, Rashkin and Turaev, they generalized the Jones polynomial of links by introducing the concept of ribbon graphs. And they are also invariants derived from quantum groups. So afterwards, it's Turaev and Viro, they introduced a path integral forms in terms of a discrete state sum, describing a wide class of 2D plus 1D topological quantum field theories, which also lead to a new quantum invariant of a string manifold. So then in 1997, an important breakthrough was Kitaev. He introduced a class of quantum double models, of which the simplest abelian version of the quantum double of Z2 group is the well-known surface code or toric code. And further on, Levin and Wen, they generalized the Kitaev's quantum double model by introducing the so-called string net models, which provide a physical or local Hamiltonian realization of all these Turaev-Viro topological quantum field theories, the unitary version of them. And this model captures all non-chiral topological orders in 2 dimensions. And the string nets they introduce in this work can be roughly thought as a planar version of the ribbon graphs discovered by Resroting and Turaev. So then it was Koenig, Kuperberg, and Reichardt. They started a class of Turaev-Viro topological quantum field theory with a modular input category, and then they developed abstract formalism in the context of quantum error correction, and they give the name of these codes as Turaev-Viro codes, which can be found in this paper. However, the study here is still relatively abstract and mathematical, and it's not very clear that how physically you can do an actual quantum error correction using this class of codes, and how to compute the threshold. And this is a main motivation of our work, that we want to find a concrete way to do error correction and to find out its threshold. So now we have done our introduction, and then we go to the concrete construction of this non-abelian code, and it's called an extended string net code, which I will explain. So in order to have a concrete physical realization of this Turaev-Viro code, so we should consider the models constructed by Levin and Wen. So this Levin-Wen model, it can be considered just as a generalization of the well-known surface code model, where you have 2 types. You define the code on a trivalent lattice, which one example is the hexagonal lattice. So each vertex is degree 3, and you put the qubits or qubits on the edges of this lattice. And then there are 2 types of projectors. One is the vertex one, the other is the plaquette one. They are similar to the stabilizers in the surface code. So one of them is 3 body, the other has 12 body. And the mathematical structure of this code is they are defined by a thing called the unitary fusion category. So that fusion category describes a simple object, which are strings, and they have labels. This string has labels or types that as 1, I1 to IN, and they correspond to the qubit states living on the edges, like 0, 1 to n. And then there are some structure called the branching or fusion rule that define the vertex operator. And then there's some extra algebraic data, the quantum dimension D and the F symbol, that determine the plaquette term. So this may sound a little bit abstract, but there's a nice thing is that so a particular example of this Levin-Wen model is just the usual, the well-known surface code. So we can understand the details of this model by first considering the properties in the surface code. So this is a slightly modified version than the usual surface code defined on square lattice, but actually surface code can be put on any lattice, which a tessellation of a 2-dimensional manifold. So in this case, we put the surface code on a hexagonal lattice. And it has 2 types of operators. Now they are stabilizers. So the Q, the vertex operator, is a 3-body Z stabilizer. And The placate operator is simplified to a 6-body X operator. So towards in general a 12-body in the Levin model, but those now become an identity operator, and then what's sit here is just a 6X. So in this case, the fusion category for the surface code is just simply a Z2 group, and it has two elements. One, which is the so-called vacuum label, and then there's an E label. So what this label means, so E corresponds to this thick edge, so which means there's a string occupying this edge. So it's an occupied edge, and it corresponds to the qubit in the one state. So in this model, instead of having qubit, you just have a simple qubit. And then this label one, the vacuum label, just corresponds to the qubit in the 0 state, and that just means there's there's an edge which is unoccupied by a string. So in general, so you can write the wave function of the ground state as a superposition of this sort of bit string, but not all kind of bit string configurations are allowed. So the one allowed is that they have to have satisfied the vertex operator, have eigenvalue +1. And that vertex operator encodes the so-called fusion rule, and that requires two E string fuse into the vacuum string. So in this language, it simply says that this sort of a bit configuration is allowed on the vertex. So if you look at the vertex, so it always has to have an even number of 1. So that just means 1 and 1 fuse to 0. And that satisfies the fusion rule here that the two E string fuse to the vacuum string. So and that obviously satisfies the parity check of this 3-body Z stabilizer. And also, it's also fine that if you have a vertex that there's no string is occupied, and the parity is still even, and set you have +1 eigenvalue of this 3-body Z operator. So if you satisfy that, then this vertex operator will have eigenvalue +1. And that gives you a negative energy in this Hamiltonian. So that means you are in the sort of in the ground state. And if you don't satisfy this rule, that you, for example, you have a broken string, that you have a string stick out, that there's an endpoint of the string, then you will have a -1 energy. Then that will lead to an energy penalty. That means you are in the excited state. So the placate term here, when you apply to a given string configuration, it can change you to some other string configuration. For example, you put it here, then you will form another string configuration. So all the allowed string that's satisfying this fusion rule is closed string, or they are loops. So the ground state, turns out in the end, the ground state of the surface code is just an equal superposition of all these closed string, all these loops. So that in physics we call it a condensation of a closed string. So it's somewhat similar to the idea of a Boson-Einstein condensate, where there the Boson-Einstein condensate is just an equal superposition of all possible particle configuration. But now instead of particles, you have this closed string, which are more extended object. So among this configuration, among this closed string, you could also have some non-contractible closed string. So you can think of this lattice as a torus that you have a periodic boundary condition. So there's some non-contractible string goes across the system, which also shown in this picture. And this is where the quantum information is stored. So if you have the presence of this non-local string, or the absence of non-local string, they correspond to the logical qubit state in the 0 or 1. So you can think with the presence you have qubit logic qubit 1 state, or without it you have logic qubit 0 state. And any local noise cannot, which is much smaller than half of the size of a system or the co-distance, cannot corrupt your quantum information. So this is an example of the quantum book I just mentioned in the beginning of the introduction. So in principle, you could also have a non-local string going in the horizontal direction. So in total, a torus topology can store 2 logical qubits, where it's basically you have the absence or presence of the non-local string in both directions. So there are 4 possible combinations. So now we sort of understand this structure in terms of surface code, and then we can move on to the more complicated cases. So just to illustrate the idea better, so now we want to create some excitation in this code. We put a Pauli operator here. So then you can see that this closed string become broken. And the endpoint of the string, they actually correspond to the anion in the surface code, which are called the E particle. And this E particle also has the fusion rule that 2 of them kind of fuse into vacuum, which can be seen from the fact that they will create together, a pair of them created from the vacuum. So the anion fusion rule just emerge as the excitation of this code. And you could do error correction if you measure the vertex syndromes. So you find their E particle there, and then you can apply a Pauli string to connecting them again. Then you fix this closed loop. That's essentially how you do error correction in surface code. And then for in the dual lattice, you have a valid placate operator where there's M anions there, and you can also apply a string operator to fix a pair of M anions in a similar manner. So now we go to the situation of some non-abelian code, which now the input category is the Fibonacci category. So and this category has 2 string label. Again, the one is the vacuum label, just correspond to the qubit in the 0 state where there's absence of a string, so the edges are unoccupied. And there's tau label, which is like the E label before, it just corresponds to the qubit in the 1 state. And now the fusion rule is a bit different. So 2 tau string, they can either fuse to the vacuum, so which is like in the previous case, the vacuum string. So 2, 1 fuse to 0 in this vertex. But there's an additional allowed possibility is 2 tau string could also fuse to tau. So the difference from the previous allowed configuration on a vertex, there were 4 allowed configuration. Now there's the additional one, which is the 111 configuration. Now you can see that the allowed string configuration in the ground state, it's still a closed string, so you cannot have any open string because that means excitation, that's similar to this case. But this string can have a branching structure of kind of a sort of a which corresponds to the fusion of these strings. So in this case, they are called string net. So that just means there's this sort of a branching structure. And now the ground state of this model, this Hamiltonian, or the wave function in our code space, is just a condensate of this string nets of this branch string, which is essentially a superposition of all possible string nets satisfying this fusion. And again, there could be this sort of non-local string to encode the information. And on torus, you can also encode 2 logical qubits with the non-local string in both directions. So that's the Levin 1 model, but there's an important difference of this the generic Levin 1 model, the Fibonacci model, and the surface code is that vertex operator and the placate operator, they don't necessarily commute. So in the surface code, they commute. That just means you could independently measure them, their simultaneous the eigenstate, just their simultaneous eigenstate of this operator. So you can do E and M correction independently. You can correct the vertex and placate of errors independently, just as if there are two independent classical codes. But unfortunately, it's not the case here. So although the ground state is actually a simultaneous eigenstate of both operator with eigenvalue +1, but the typical excited state is not. So the placate operator only have well-defined eigenvalue if all the vertex operator is satisfied, which means they satisfy the fusion rule and the vertex operator has +1 eigenvalue. So that's so the essential difference. And so in this sense, the Hamiltonian of the Fibonacci non-abelian model is a frustration-free Hamiltonian. So so the ground state satisfy those local projectors, but the excited state don't have a simultaneous eigenvalue of them. So then we are essentially study the case how to do error correction of this frustration free Hamiltonian. So now in order to proceed to do actual error correction, we need to modify this Levin-1 model or the string net model a little bit. So what we do is we add an edge, a tail edge. We call it a tail in each placate. So there's a qubit sit on that. And then this edge also divide your original vertical edge into two edges. So it in fact introduce two additional qubits in each placate. And so you have a new set of vertex and placate projectors. The vertex projector is still 3-body because it's on each vertex, and each vertex is still degree 3, so it's 3-body. But the placate operator becomes 16-body. So there's an important property of this code is that there's a so-called string net subspace where all the vertex operators are satisfied. So they have eigenvalue +1. That just means there's no broken string. So in this subspace, where all the states are still string nets that are not broken, then the anyon charge inside each placate is actually a well-defined quantum number. And we could just measure this anyon charge, and that will be the syndromes of our error correction. And also, it's sort of equivalent. So measuring this anyon charge is also more or less equivalent to measuring the placate operator, although it contains more information than just the placate eigenvalue. So as a warm-up of the actual error correction, so we first discuss how to fix the vertex error. So now imagine there are some Pauli errors acting on the edge. So one type one should consider is just the Pauli X operator. So this Pauli X operator will violate in general violate this vertex operator. So here you can see there are 3 vertices violated in this example. And then you have a broken string net, which is outside the string net subspace. But one could actually measure all these vertex operators, just like in the surface code, you measure the vertex stabilizer. And in addition, you also measure the tail qubit. Condition on these measurements, it turns out you can always find some unitary, UV, condition on the measurement outcome V, that pull the string back into the placate. So you can always trap the string locally into this tail. So that's why we want to introduce this tail structure, because you could always fix this vertex error using this trap procedure. And we can have a concrete quantum circuit to measure and fix this error. So the circuit to measure the vertex operator was actually proposed by Bonstein and DiVincenzo. And DiVincenzo was also working at IBM for a very long time. So for example, in this case, when we consider a single segment in this dash box, we have 3 vertices, the top, middle, and bottom. And we can use the same circuit to measure each of them. So to measure them, you have these 3 black dots, which are the data qubits in the code. And then you have an extra ancilla qubit, which is the white dot here. And you apply this circuit, that can tell you whether the vertex is violated or not. So the first 3 C knots just is to deal with the case that there's a broken string here, which means there's one of the edges occupied by a string and the other is not. And that will just, when it goes through any of these 3 C knots, it just will flip the ancilla qubit. So you can capture that if there's a single a broken string. But remember, we also allow the case that all of them are occupied string, that you have a branched string structure in the string net. And that is allowed. So, if you have these 3 C knots, that will flip the ancilla qubit odd number of times, which is basically meaning you flip it from 0 to 1, and that's not what you want. So, but when all of them are highlighted, occupied, you just trigger this Toffoli gates, because all of this is in the one set, and then you flip the ancilla again. So that just flip the ancilla back to 0, and you don't detect there's a vertex error, and that's sort of consistent with what we want. And then based on the vertex measurement result on each of the vertex, then you can apply certain conditional unitary circuit. And here I'm just showing an example that you have a top and the bottom vertices being violated. There's a single broken string with 2 endpoints. And then you can use this unitary just to always to trap this string. So if there in all of this possible configuration, you can always trap this string into the puncture, into the tail. And also in some cases that it just simply delete the string. But in all cases, there won't be any violated vertex. So up till now, we have know how to correct the vertex errors. So I just want to make sure, is there any question from the audience if up to this point? Because I will proceed to later section.
Hey, so we had a bunch of questions, but actually the people watching did a really good job of answering each other's questions, which is why I didn't want to interrupt you yet.
Okay.
So I think we're good to proceed, but I'll keep my eye on the chat.
Okay. So now we can fix this vertex error and bring them to the string net subspace, which there's not any string being broken. And then we can have well-defined anyons, the quantum number of the anyons in this subspace. And we are gonna try to measure this anyon, and these are the syndromes of our error correction. So in order to describe that, we need to introduce some additional structure, which is this ribbon graph defined by Rashkin and Turaev. And this ribbon graph is just can be considered as the generalization of the string nets where we just discussed. So those string nets are living on the edge of lattices. So it's somewhat a discrete object. But this ribbon graph, instead, they can live in a continuum. So they don't have to be pinned onto the lattice. And they are defined mathematically in the similar way as the string net, that you have to have an input unitary fusion category with a set of string labels to label this ribbon graph, like these labels K, G, H, L, and they could have these string types. Again, this one is the vacuum label. And they have to satisfy a set of fusion rule, and there's additional algebraic data to define them. And they are defined on a compact or n-fold manifold, which can also have boundary. So in this case, we show these punctures, so each puncture will have a marked point here. So the definition of this ribbon graph is they are labeled and a direct graph, which means there's some arrow here indicated the direction, and they are embedded in the manifold. So the requirement is that in the bulk, this ribbon graph has to be a trivalent graph, which means each vertex has degree 3, which is consistent with the lattice of the Levin-1 model, which we defined earlier. And they have to satisfy the fusion rules we introduced before. And then there could be a vertex have degree 1 that on the max point of these punctures. So on the puncture, you could have a univalent vertex. And that's essentially the reason why we introduce those tail edge. That just make sure you can always trap this ribbon graph or the string nets into these punctures. So the Hilbert ribbon graph Hilbert space H sigma defined on the manifold sigma is a linear combination of ribbon graphs, similar to the linear combination of string nets in the ground subspace of the Levin-1 model. And it's the linear combination modular the following local relations. So this local relation means, for example, the first one means if you bend the string a little bit, for example, here you bend the string a little bit down, and that represents exactly the same ribbon quantum state. So the two ribbon graph with local deformation correspond to the same quantum state. And that also means that since your wave function is a superposition of all possible ribbon graphs, just like in the string net condensate case, that also tells you the wave function amplitude of these two ribbon graph configuration differ by local deformation is completely the same. The wave function amplitude is the same. And then there's this second rule just means there's no tadpole configuration allowed in the bulk. And that can be understood as because the wave function in this Hilbert space is a fixed point wave function, means they are scale invariant. So you can zoom in and zoom out. They always look the same. So if you shrink the bubble here, so you zoom out, this bubble will just be shrinking to a single point, and you get a broken string, which is not allowed in the bulk, that violate the fusion. So this J always has to have the vacuum label, and then you just have a single bubble, single loop is allowed, and it turns out you can this ribbon graph is equivalent to basically nothing there, so you can shrink it into nothing, but get a prefactor, which is this D, and that's called quantum dimension in this theory. And the third one, which is the most important one, which we will use a lot later, is the so-called F move. So it's a recouple relation between these two ribbon graphs. It tells you that locally a ribbon graph has this structure can be expressed as a superposition of a ribbon graph with a different way to connect these four legs. So you can first couple these two and these two, and or you could first couple these two. And just to show you an example, so you can transform this current ribbon graph by flipping this G edge to another ribbon graph, basically flipping this edge shape. Keep the four legs the same, but flipping the central edge, so G to N, and then you have a sum of N. So this local relation just tells you that there's a relation between wave function amplitude, and then you can express the one ribbon graph in terms of other ribbon graph. So they depend on each other. So although that just, when you modulate this local relation, that just gives you a finite dimensional Hilbert space. Although it looks like an infinite dimensional, there's infinite degree freedom to begin with, because you have a continuum, you have all possible ribbon graphs. But once you modulate this relation, that just become a finite dimensional space, and that depends on the topology of your manifold. For example, the number of genus of the manifold, the number of punctures. So only those ribbon graph, for example, has a non-contraptible cycle going around torus, and you have another ribbon graph which doesn't have that non-contraptible cycle of ribbon going around. They cannot be related to each other. So the degree of freedom is encoded in these non-local ribbons. So so to understand it better, we again can go back to the toric code or surface code case, and this relation just tell you the relation that you can also locally deform the string, and you can shrink the bubble to nothing, and that's equivalent to multiplying the plaquette stabilizer. And also you could recouple two ribbons in this way. Again, that's equivalent to multiplying this loop, which is also a plaquette stabilizer in the center. And that's essentially a homology relation in topology. So the surface code is completely mathematically equivalent to a Z2 homology theory due to these relations. So in the case we focused on today, the particular model, the Fibonacci Turaev-Viro theory. So the F move have the following structure. So that's all the transformation when you switch from one ribbon configuration to the other. So again, this thick edge is just the occupied string. They correspond to the tau label, and then there's an unoccupied edge corresponding to the vacuum label. And this configuration can be expressed as a superposition of the other two, that the vertical edge is either occupied or not occupied. Same for this configuration. And for the rest of them, there's only one possible outcome, because they have to satisfy the fusion root, and the only possible outcome is, for example, in this case, this edge has to be occupied without break this string. And this coefficient of phi here is the golden ratio, which is also the quantum dimension in the Fibonacci alien model. Okay. So now we have but actually, so this F move can be implemented with a quantum circuit. So you consider you can put 5 qubits on these edges, and then this dash box just correspond to implement the part for this non-trivial part of this F move. So you have the 4 qubits in the one state, and they correspond to this tau string, and that will trigger this Toffoli gate, and that implement a rotation according to an angle which is the arctangent of this golden ratio. So that creates this sort of superposition. And the rest of the circuit just take care of the other transformation. So actually, you could just implement this F move with a simple quantum circuit. And so now we could relate this ribbon graph subspace to the string net subspace we talked about, which was defined on the lattice. So, and they satisfy all the vertex operator. And the relation, you can relate them just by simply, you consider there's a punctures inside each plaquette, and then our tail was just to trap those strings into the puncture, and these ribbons here are blocked by this puncture, and so to relate them, you can simply pin this ribbon onto the edge of this lattice, and that gives you the string net living on lattice. And now we could represent the ground state wave function just with this ribbon graph language. So the plaquette operator in this model simply corresponds to add a particular vacuum loop a particular ribbon around the puncture inside each plaquette. So this vacuum loop is basically a superposition of all possible string type with a prefactor of this quantum dimension of each string type. And in the case we focus on the Fibonacci Turaev-Viro model, it is basically a superposition of an unoccupied ribbon, the vacuum ribbon, and the occupied ribbon, which corresponds to qubit in 0 and 1 state. Then you can check that if I apply the plaquette operator on this configuration with a vacuum loop around, that just add another vacuum loop. And then after some math, you can find that they just, again, simplifies to a single vacuum loop around this puncture. So this configuration has eigenvalue +1. Now we can just write down the ground state wave function and using these ribbon graphs, and they are simply this vacuum loop around each puncture. That's how you represent the ground state wave function. It is great ground state because it satisfies this +1 eigen. They have +1 eigenvalue of this plaquette operator, and they will also have +1 eigenvalue of the vertex operator. So what you can turn this ribbon graph state to the string nets by applying some F move, and that will somehow pin the edge onto the pin the strings onto the edge, pin the ribbons onto the edge. And then you get the string net wave function, which is a superposition of all possible string nets. And that, of course, the F move set will always preserve the fusion rule, and that will satisfy the fusion rule, and hence the vertex operator. And your logical information is actually encoded in a non-local ribbon that's wrapping around the torus. And if you bend it with some local deformation, that's also represent the same wave function. After introduce the ground state, now we can finally think about the excited states, which which describe those aliens. So it turns out the state in the ribbon graph subspace H sigma, they include those ground states, but also the excited states, which are the fusion states of aliens of a so-called doubled category. So this double category is essentially a tensor product of the two qubits of your input category. So the alien labels here will have a double label. So in the case that we have a Fibonacci model that will have two string types, the alien will have 4 types. Basically, it has 2 labels, and this 1 is still it means the vacuum sector that there's no alien present, and then essentially you have 3 types of non-trivial aliens. And then we can show that this ribbon graph can not only represent the ground state, but also the excited state. So the excited can be explicitly or exactly represented by these ribbon graph states with these red ribbons. So this red ribbons is equivalent to a double ribbon, which have these 2 labels. So each label could either be 1 and a tau, which from the Fibonacci category. And so this thick label just means there are 2 labels there. So your excited states actually just is corresponding to this doubled ribbon graph. And so these punctures, they are just those punctures living in the center of the plaquette where we introduced before. There's some extra complication is that these 2 ribbons, they can circumvent this vacuum loop around the puncture and then recombine into a ribbon and going back to the puncture, which has this leaf label L. And this label has to also satisfy the fusion rule of this category. So in this case, you have this extra label that also split your type of excitation into 5 types. So besides the double label, that if both label is tau, then it could either fuse to the vacuum or the tau label. So so the total alien sector split actually into two types A. So and then including this leaf label, there are 5 type aliens sitting in each puncture. So then we can also put this ribbon graph state onto the lattice. So without the aliens, our wave function is just represented by these vacuum loops around each puncture. That's our ground state. But then when there are aliens, so what you have is a ribbon graph state like here. And what actually it means is that so this each red ribbon is a double ribbon, and you can think of that it's equivalent to 2 copies of alien models, like 2 copies fractional quantum Hall states. And there are some Fibonacci alien leaf above the lattice, and that corresponds to the ribbon above the lattice. And there are also some ribbons going underneath the lattice and travel through that. That's correspond to the other label. It could also be 1 and tau. And then they combine and trap into the puncture, which more precisely can be represented by a cylinder in the center of each plaquette. So that's the full description of the aliens in this model. So it's a bit elusive because these ribbons are not actually living on the lattice, on the edge of the lattice or the qubits. So it seems it's impossible to really measure or capture this alien excitation, because what characterizes these types are the labels on these ribbons, and they don't live on the lattice. But it turns out there's some magic here that you can do a unitary transformation to transform this double ribbon graph into a planar ribbon graph that each ribbon only have a single label, 1 or tau. So now it again becomes planar. So that just means you could actually try to deform lattice to have this extra shape, this extra edges, or with this kind of snail-like shape. Then you could just measure these qubits on this extra component of this snail shape. And from these labels, you can infer the label of the aliens. So that's sort of a magic going on. And then that's the essence of how we will try to measure these aliens. Let me skip this slide. So that just means you can also define a state on a torus, and there's some non-contraptible loop. And if you have some error that going let you create some alien travel around this handle, that induce a logical error. And that's something we want to prevent. So now in order to really measure them, we need the so-called tube algebra from the topological quantum field theory. So this tube algebra contains a tube operator, which is essentially can be considered as gluing a tube onto the puncture of your lattice. So you can just glue it here, and then you can so that this tube or a cylinder is a topological equivalent to an annulus. So you can deform it into a planar structure. And then you can further just redraw this shape, then you find that's just sort of the snail shape we just shown above. So then actually this tube algebra tells you how to write down the projectors of into each alien sector. So we said there are 4 types of aliens, and one of them could even split to additional 2 types. But there are so-called central idempotents of this tube operator. They are just a projector into each alien sector. So for example, the 1-1 sector is just our vacuum sector, and that projector just is equivalent to the plaquette operator. So so if you express them here, so you can see that it's equivalent to add a empty loop with an occupied loop, and that was the definition of this vacuum loop. And similarly, you can have the expression of the other alien projectors just with these 4 edges. So this is where your qubits will live on. So the beauty is that by apply certain transformation on these 4 qubits, so then by doing projective measurements of these 4 qubits, you could just project your state into a definite alien sector. So in general, if you have some sort of an alien excited state, it will be in a superposition of different alien sector. But once you apply the unitary and the measurements of these 4 qubits, it will be projected into a particular alien sector, and you know what sector they are. So that's how we do the project measurement of these aliens. So now we want to define have a more precise definition of this tube operator. And as we said before, that the action of the tube operator to the lattice is just equivalent to gluing this tube onto this puncture. So it has this shape. So you could derive the expression of the tube operator by doing some local deformation. So we can start with this tube configuration, and then what we do is apply a sequence of F moves. So this defined before. So this F move can deform your lattice. It is a sort of a co-deformation that it can gradually move this edge around and finally shrink it into your original lattice with a tail. And then by combine this F symbol together, you just derive the expression of the action of the tube operator. So it's actually a product of F. And one particular example of this tube operator is just the placate operator, and it's also a product of these F symbols. So now finally we want to measure this alien charge. So how do we do that? So that's actually the opposite procedure of how we derive the expression of the tube operator. So what we do is we want to apply a quantum circuit to grow this tube shape or this snail shape onto your lattice through a sequence of co-deformation. So what we can do is we start with this tail lattice with 3 additional ancilla qubits. And then we apply some signal to entangle this ancilla with the original qubit, and apply some single qubit rotation to prepare a loop diagram, which is sort of a smallest string net state. And then you can apply this F move to flip this edge. That will absorb. So that will absorb this loop onto this tail. And you can further apply a sequence of deformation of this F move that you can sweep this edge around, and then it creates this tube shape. So that's the quantum circuit we show here, where this blue box is just a circuit we introduced before to describe those F move, is describe how to grow this tube. And then you do some projective measurement and unitary on these ancilla qubits, and you further measure out these ancilla qubits. Then you could extract the charge and also project the state to a definite alien charge state. So the whole error correction protocol can be described in the following way. So you apply the environment applies certain noise to your system, and you measure the vertex operator and apply vertex correction to bring your system back to the string-net subspace, which has well-defined alien charge. Then you measure all the alien charge in each placate, which give you some syndrome. Then you try to use a decoder to fuse these aliens that bring them back into the vacuum. So if they are not empty, you further measure them and repeat procedure until all the aliens are cleaned up. So here I'm showing a simple decoder called a clustering decoder does this job. So what I show here is a decoding graph. So the vertex of this decoding graph, so it is a dual lattice of the original hexagonal lattice where we define the Levin model. So remember, the alien will living inside the plaquette of the Levin-1 lattice model. And in this dual lattice, they are just living on this vertex. So after applying the noise, we create a set of aliens in this system. And we can measure them and extract this alien charge. And then we prepare a local cluster around each alien and merge the neighboring cluster together. So for all the aliens in the same cluster, we just merge them together and kind of move them into the same site. So if this alien turns out to emerge from the same fusion tree we showed, they popped out of the vacuum together, and then they will just annihilate into the vacuum. So, but if there are some additional ribbon connecting these two aliens, like what we showed before, so they will not annihilate because they belong to a different cluster. And then next you further grow your cluster by one lattice constant, and then merge the neighboring cluster. Then you have a larger cluster, and you are supposed to merge the aliens in the same cluster again. So if you're lucky enough, that you just correct the error. But if you're unlucky, maybe there's a ribbon going around in the other side, wrapping around the torus, and then you could annihilate this alien, but you create a non-contraptible ribbon across the torus. That just leads to a logical error, and your decoder fails. So finally, we ask, now we have the error correction procedure and the decoder to decode the error. So how do we get an error threshold from a classical simulation? So the central idea is to translate the qubit errors into some anionic process. So you could use your classical quantum computer, to represent the whole wave function of the set of qubits. And that has an exponentially large Hilbert space, which grows like 2 to the n, where n is the number of qubits. And you could simulate in this way, but that's highly inefficient, because if I have some very sparse noise and I create a set of aliens in the system, and these aliens, the only degree of freedom are just the charge of this alien. So for example, this label A and B, and for example, this B, which is kind of the total charge of these two A, and could be in a superposition, and that leads to a finite Hilbert space. But it's very small compared to the full Hilbert space of the entire qubit system. So a much efficient way to simulate it in a classical computer is to choose a basis, which is the alien fusion basis represented by this ribbon graph state. So the only degree freedom are just containing these charge labels. And this anionic fusion state, they form a complete and orthonormal basis of the whole stringnet subspace, where there's no string being broken in the bulk, and they are all trapped into the puncture. So then it turns out the action of the noise and the following measurement and correction we apply to fix this vertex error, they can all just be described in the anionic fusion basis. And then the only thing you need is to calculate this matrix element. So for example, you could start with your state in the vacuum sector, which means all these alien labels are just in the vacuum label 1, 1, and all of this is 1, and you're in the ground state. But after you apply this Pauli error, which is noise, then and also the following up measurement and correction, you could have a certain amplitude to transition to some alien state, that is some alien being created. And you just need to calculate these matrix elements to simulate the whole process. To be slightly more concrete, you have certain initial state. It could be the ground state or some already excited state with some aliens. Then you could apply the errors on this state. And then you can evaluate the probability of the measurement outcome of this vertex measurement, which we performed before. So we know each vertex could either be valid or not. And what's the probability? You can calculate it just by this matrix element. And this probability will be fed into our classical computer because we need to do a Monte Carlo simulation of this error correction. And there's some probability you get some outcome for this vertex projectors. And that's given by this number. You just throw a dice, and then it tells you what's the measurement outcome in this process. Then conditioned by this measurement outcome, you apply some unitary, and that just give you the wave function in the next step. So after you're applying error measurement and the correction. So what you need to calculate is just this matrix element. It tells you what's the transition element from one Anion basis to another Anion. It tells you whether some Anion created or annihilated or moved around. So that's what this. So the only thing you need to do is calculate this matrix elements. It turns out there's a nice property that this matrix element or the action of these noise operators only dependent on the local property of your anionic fusion states. Basically, it only cares about this anion charge in the neighboring plaquette of this Pauli operator. So you only need to calculate a finite number of them. So there could have other crazy fusion tree around, but they won't affect the calculation of the matrix element. And in order to do that, so we need to find an efficient way to calculate this matrix element. It turns out you cannot just naively use the string net wave function because we don't even have that. We know the ground state wave function is a superposition of string nets, but it's not easy to know their amplitudes. But there's an efficient representation using this tensor network state, and you can also encode this ribbon graph structure into the tensor network state by building explicit this tensor network structure to take care of this ribbon. And that allows you to calculate all these matrix elements. And there's some additional comment is that whether you could even simulate an Anion model, which is itself universal for quantum computation, because we know that the Fibonacci Anion model is universal. So then it seems that simulate a generic Anion dynamics of this Fibonacci Anions is equivalent to simulate a universal quantum computer. And that must be classically hard. The results must grow exponentially with the system size. But actually it turns out to be not the case for our purpose because we are simulating the error correction and the error rate is small. So it's below the error threshold. So what we want to extract is the error threshold. So you just need the error probability to be slightly above the error threshold or below that. And in those cases, those errors just create this disconnected Anion fusion trees. So this Anion from the same tree, they pop out from vacuum together. And your total system wave function expressed using the Anion fusion basis is just a tensor product of this individual tree. And turns out when you are below the percolation threshold, the typical size of this fusion tree is just a logarithmic of the system size. And the error threshold is typically in the region that much below the percolation threshold of these Anions. And then a exponential of this logarithmic L turns out to be Pauli of L. So it's polynomial to complexity to simulate the Anion dynamics in the error correction process because they are kind of disconnected. So with all this, we just finally specify the assumption of our simulation. So we assume the noise is represented by random Pauli errors that it has equal probability of X, Y, or Z. And then for technical reason, we apply the errors sequentially. So the total number of errors applied to your system satisfy Poisson distribution, with the average being the error rate on each edge times the total number of edges. And we also assume perfect measurements and a perfect quantum circuit to perform the recovery operation. And we simulated the dynamics of the total T steps, which is each step you apply an error, and with a randomly selected edge and a random Pauli error. And then, as we discussed before, we perform vertex measurement and recovery to bring you back to the stringless subspace. And then you measure the annealing charge. So that's the full list of things we simulate. And finally, we can get the numerical results for the code capacity error threshold of this Fibonacci Turaev-Viro code. So from here, you can see that these curves cross at 4.7. That's the error threshold. So for the code capacity noise, and it turns out this code also favors some bias noise structure. So if you have a pure dephasing noise, then you will have a 7.3% error threshold. So this is actually comparable to the surface code thresholds under similar condition, where it's slightly above 10%. So although the code seems to be complicated to some extent, it actually has quite a good memory threshold. So here's our summary. So we consider non-abelian error correcting code, which is on a system of ordinary qubits, not Majorana qubits or topological qubits. And the code space is defined by an extended Levin-1 string-net model. And then three ingredients where the quantum field theory and including this tube algebra and anionic fusion basis is important to describe our error correction process. And the Tensor network was used to translate the qubit errors into some probability of generating annealings. And this is gives the first threshold for a 2D quantum code, which is universal through braiding of non-abelian annealings in 2 dimensions. And the threshold is comparable to the surface code. And we are actually, one successful thing we achieved is that we translate very abstract process in the topological quantum field theory just into processing quantum codes and quantum circuits. So make a very concrete realization of these abstract ideas. And there's some outlook is what to do next. We can try to simulate fully the fault-tolerant setup, including the measurement and circuit level noise. And also find a better decoder and simplify the error correction scheme. So actually, the quantum circuit of measure annealing seems to be quite complicated. Well, as what you see before, and as many F-move circuits. But recently, we found there's actually a way to greatly simplify them to greatly reduce the number of these F-moves needed. And one can also try to find the simpler non-abelian codes and consider cases where this code has boundary instead of being defined on a torus. And these techniques can also be used for a quantum simulation process to simulate this Turaev topological quantum field theory, or even loop quantum gravity, because this loop quantum gravity has the spin network structure, which is very similar to the string nets or the ribbon graph structure mathematically. And one very important thing is the road towards experimental implementation. So from my perspective, it's not very difficult to prepare this Levin-1 ground state in a NISQ device. Just slightly more complicated than preparing the torical or surface code states, but not too much. But then, in order to do a full error correction with them, one also need to improve the implementation of this multi-control Toffoli gates, which is used a lot in these F-moves. So it would be nice to have some hardware-efficient implementation of these multi-qubit Toffoli gates. So potential direction could be candidates could be this Mormon-Sorensen multi-body Mormon-Sorensen gate or Rydberg blockade, where you can directly implement these multi-qubit gates instead of decomposing them into 2 qubit gates. And there are also ways to simulate to mimic these gates in like circuit QED architecture. So that is the basically the end of the talk today. So thanks very much for your attention, and I would like to answer any questions if you have.
Thanks so much for that great talk. Yeah, so we had a couple questions that were, again, sort of answered in the chat throughout, and we're a little bit short on time. So I think I just want to ask one question. So my question is, could you talk very briefly about the next step, I guess, in the process and what you hope to see sort of in the near term?
So yeah, as I mentioned in the outlook, so but one from the theoretical perspective, so here we get this error threshold as assume perfect measurement and perfect circuit. So that's very close to surface code. But then the next step is first you include the measurement error, and that will potentially brings down this error rate a lot. And it would be like we would like to see how close it will be to the surface code and a similar assumption with a measurement error. And then also include the full noise model, including all the circuit level noise. So right now, surface code has this fault-tolerant threshold with slightly below 1%. And I wouldn't expect that it would be very close to 1%. It could be probably one order of magnitude lower than surface code. But because of the computational power is nice, it can do universal gate in 2 dimensions. So it's still worthwhile, even the fault-tolerant threshold is lower than surface code. The question is how low it is. And the other is towards the experimental implementation I just mentioned before. So the main challenge, as you can see here, so there are many of these blue boxes, and recently we found a way to reduce them. So you probably just need 2 or 3 blue boxes here. But each blue box also has some challenging Toffoli gates. And if you decompose this Toffoli gate into 2 qubit gates, there will be a lot of them. So the question is, well, either you have some better way to have a circuit compiling to implement these Toffoli gates, or you probably want to directly implement them in the hardware. So like what I mentioned, probably use something like Mormon-Thorson gate type of collective gates. So that I think is important for the experimental part. But I would think that just to prepare the ground state of this code is much simpler than to use it for error correction. So that could be done in the NIST error.
Got it. Okay. Well, this was super interesting. So thank you again for your time and for being here with us today. So I think we're just going to wrap up here with that. So again, I want to thank our speaker, Guanyu, for being here with us and giving us his great talk. And for everybody who's participating in the audience, we had a pretty lively chat today. Everyone remember to subscribe if you're interested in hearing more from our research scientists and members of the academic and research community. And with that, we'll say thank you again, and everyone have a great rest of your day.
Thank you.